Okay. So then of course now you guys know how to design OTS, you know how to increase again. You can make multi-stage OTS, you can compensate this, make it stable in negative feedback. So ideally if things were all nice and good, once again the course would have ended here. But unfortunately for you guys, unfortunately for me, that's not the case, because there are a whole bunch of other issues to tackle. And one main issue with the kind of circuits that we have seen is the following. Especially this is problem in on-chip implementations. And I'll just briefly mention the problems without getting into a lot of details, and we'll see the solution. So let's say one of the problems can be this. So let us say you have an analog signal, a sensitive analog signal that you want to connect from, let us say, a sensor output or somewhere to another circuit. You basically connect it using a wire. But of course, a wire, it's a 2D, but you're going to have a metal like this. Now on the same chip, you might have, let's say, clock signal getting routed. So from, let us say, from here to here, you're also routing the clock. Let us say this is your signal V in, this is V clock. So V in is a sensitive signal, very low frequency or a very low amplitude signal. And you have clock like this going from 0 to VDD. Okay, this basically what I'm saying is this amplitude might be a couple of millivolts maybe, whereas this can be about 100. Now anytime you have two metals running in parallel, what happens? What forms? Capacitor forms. So which means, remember that anytime you have this jumps, so this jumps corresponds to low frequency or high frequency? High frequency. At high frequencies, what can you say about the capacitor? So if this is going to be a short at these transitions, what will happen now to the signal? This is V in and V clock. So as you guys mentioned, at these jumps, we are going to have a very high frequency component. So which means the capacitor will act like a short circuit. So what will be the signal you get here now? How will it look like? Sorry? Yeah, basically each of these jump will basically couple here. So you will have something like this. So at each of these peaks you will have something. Okay. So this will basically corrupt your entire signal, because this already I told this can be few millivolts. So this is a problem, right? So this basically, I'll just write it. So interfering signals can be a problem here. Okay. Now second problem is this. See, as I already mentioned in the first lecture, in practice, any electronic system we have, it is not truly analog or truly digital. It is a combination of analog, mixed signal, and digital circuits. So let us say here you have some analog circuit made using an opamp that you designed. So it is connected to some supply and ground. Let us say you have some other circuit, some digital or mixed signal circuit connected to the same supply and same ground. Okay. This, let's say for example, it's a digital circuit. Let's not confuse so much. And you will be connecting the DC supply off chip. Right? So this is basically the boundary interface. From here you will have basically connected. I will not show it this much, so I will show it this much. So this is, let us say, the interface. Now of course I have drawn nice short circuit like this, but in practice this is not going to be a short circuit. What will it have? It will have internal resistance, but in addition to the resistance, what will it have? I mean, capacitor is formed between two parallel lines. If I just have one metal line, it has a resistor, and what else can it have? It can have an inductor. And as you guys already know, if you have a digital circuit which is operated at a clock, let's say it's a CMOS circuit. So when will it draw power? When will it draw current? it turns out, I mean, yeah, CMOS digital circuits or mixed signal circuits typically draw current only at the clock transition. So at every clock transition, let us say you are going to draw some current like this. See, something I'm just randomly sketching it. Let's say every clock edge it is drawing some spiky current like this. Okay. So which means this is that current. This current has to flow here, and you have a spiky current getting dropped across this impedance, right? So if let us say you have a spiky current flowing through an inductor, what can you say about the voltage drop across the inductor? What is the voltage across the inductor in terms of the current? L times di by dt. Now if the current is going to have spiky jumps like this, what can you say about the voltage? It's going to, I mean, it's not step, right? I mean, okay, forget about step, but if let us say this is going to have spiky currents, what can you say about the jumps? Will it be small or will it be large? It's going to be very large. So which means the actual supply your analog circuits will be seeing will not be your constant VDD. It's going to fluctuate a lot. Now, of course, one trivial solution is the following. What can you do to make sure that the DC voltage doesn't change? You can go and put a large capacitor. We call this bypass capacitor. So, I mean, the larger the capacitance you use, the better it will be. Correct? Again, remember, capacitor is like an voltage source. Infinitely large capacitor is an ideal voltage source. So, in principle, if you want to mitigate this, you want to have an infinitely large capacitor, but of course, you can't do it. So, you do put a capacitor and reduce it, but it's still not going to be fixed. So, the supply you see for your circuits will fluctuate like this. So, I'll say that the supply is going to have supply noise. Is that point clear? Just wanted to, convey that when you have on-chip mixed signal systems like this, and whenever those circuits draw spiky currents, those spiky currents, when they pass through the inductance you have due to the connecting wires, that will introduce a large jump. So which means the supply your circuit sees is not going to be the constant supply VDD. It's going to change a lot, and that's what we call a supply noise. Yeah.
Won't the digital circuit get affected if there is any quick change in input?
Why will that get affected?
Because it stores the voltage.
No, this is only the supply, right? There is no digital signal getting stored. This is only the supply. I mean, remember this is the VDD, right? It is not like I'm going putting at the output node of a digital circuit. That is basically a complete kill. This is only at the supply line. So now let's see the op-amps that we have designed. How does it react to any disturbances in the supply? Right? Again, the assumption is the supply disturbance is going to be small because hopefully you have put a good capacitance. So the disturbance is not really large, but it is a small signal disturbance. And for that, I'll take our 5 trans to OT as a test vehicle. So I'll quickly sketch it. So this is your PMOS stage. And you have diode connected it like this, and you have the NMOS diff pair. Let's say for now it's an ideal current source. This is going to be the output. Now the point of interest for us is to see if there is any variation in the supply, how much of that variation is going to get impacted in my output, right? Because I want to see if there is a supply noise in the final circuit, how the OTA is going to respond to that. And ideally, do you want any noise in the supply to be reflected at the output? Don't want it to happen, but let's see what happens. Right? Again, let's assume that, again, the way to deal with this is, we'll assume that the signal we have is a small signal jump, call it Vn of t. Small signal, so again you can use linear principles. So I'll assume that by superposition I'll ignore other inputs. Now I'm interested to find what is my Vout. How will you find it? Yeah, I mean you do small signal and then you use KCL, is it? Yeah, you can find the short circuit GM and R out, nice thing. But Again, remember we have looked at this 5T OTA for such a long time. So is there something you can do to simplify this further? Hmm? Uh-huh. Can you elaborate? Yeah. Yeah, yeah. Yeah, I mean, as he's pointing out, we know that this is asymmetric, although this is asymmetric. When can you claim that this will be symmetric? That is, if I have the same VGS for the NMOS transistors on these sides, as well as for the PMOS transistors on the two sides. Now, do you think the transistors have the same VGS here? Yes or no? Yes? I mean, both the gates are grounded for the NMOS, source is common. For the PMOS also, the gate is shorted. So, although this is asymmetric, you can think of it as now a symmetric circuit, because these two node potentials, how will they be? So again, without telling anything, you go and short it. So which means now we can reduce the circuit. So I have 2x of the PMOS here, 2x of the NMOS, and let's say have the current source. And for small signals, the current source is open circuit. Right? So here is where you have the N of t. And remember that this principle of using the symmetry thing, that is valid even for large signals. So yeah, okay. So anyways, now we have got this. So now tell me what is V out of t now. Remember, this is an open circuit. Okay, we have the current source. This is open circuit. There is no current flowing. So what is V out of t then? 0. Yeah. That right? I mean, other way to see is, now you have a linear circuit. This is a resistance with some value, and this is going to be some other resistance. Resistive division. What is the resistance looking down? Infinity, because it's open circuit. So all the voltage is going to drop across this fellow. So which means this is completely V. Correct? Of course, even if you find the short circuit GM and R out, you'll get the same thing. I'll give it as an exercise. So, which means whatever disturbance you have at the supply completely gets reflected at the output. Is it a good thing or a bad thing? It's a bad thing, right? So yeah, that's a problem. And to quantify how much of the supply noise is getting affected at the output, we have a term. So that is called power supply rejection ratio. Just a jargon, often abbreviated as PSRR. So the definition is this: the PSRR is the actual differential gain you have in your circuit by the gain from your supply. So you take the magnitude and typically express in decibels. So in the 5T OTA, what is the actual differential mode gain we have? What is the actual signal gain we have here? That is the input to the output. From these inputs to the output, what is the gain? Yeah, let's say it's GM of the NMOS times. Great. And in this particular case, what is the gain from the supply to the output? So ideally, how do you want this PSRR to be? Very small or very large? I mean, you want this factor to be small or large? You want this factor to be small or large? So the ratio should be? So ideally, you want this to tend to infinity. But of course, as we see, the actual circuit opamp that we have seen is not great because it is highly sensitive to the supply noise. Now I can make the same argument for the ground also, because even at the ground side I'll have a similar setup. So I'll have disturbances on the ground line, and that will again get impacted at the output. So in short, the current op-amps that we have seen, they are kind of sensitive to, I'll just say sensitive to supply, ground, and any kind of common mode interference. So let's see what can be a fix to that. And this is particularly problematic on chip, right? So let's see what's a simple fix for this. And for that, let's look at this itself. See, now remember that the actual problem is not with the output signal here, because any input you feed here, that's going to come properly here. The problem is with, let's say, the supply and the ground lines, right? Because the supply and the ground lines are shared by all the blocks. Since it is shared by all the blocks, everyone is going and dumping their garbage on those lines and making these lines not clean. Whereas if I only look at the output here, it is going to be a faithful reproduction of the input, correct? But the problem is the following: the output voltage, we are defining it as the potential difference between this local output line and the global ground line. Right? Now this line is local to the block, so it is okay. Whereas this line is common to all the blocks, so you have a lot of disturbances here. Correct? So if you want to eliminate any effect on the global lines to my output, what do you think I can do? You have seen this before, maybe, I don't know. I'll remove all this. See, as of now, my output is defined as a potential difference between two lines, right? One is this local output line, which is okay. The other line, the reference line, is the ground line, which is common to all the blocks. Because the other line is common to all the blocks, we are having this issue, right? So as a fix, what can be done? I mean, output has to be defined between two, potential difference has to be defined between two lines, two nodes. I am saying one node is local to the block, so it is okay. The other node is common to all the blocks, that is the problem. Right? I mean, already it's getting transferred here, right? What you're saying?
Same disturbance in that output,
Mhm.
the output disturbance cancelled out. Same disturbance, the same pattern is.
Okay, I mean, okay, I don't know if this is what you mentioned. See, the final, I mean, the actual idea is this: you now have two lines locally to the block, and say that my output is now going to be defined as a potential difference between those two lines. Now the idea is, anytime, let us say, the ground changes. Ground is a reference node, right? If this node changes, this node will also change by the same amount. This will also change by the same amount. Because remember, ground is a reference potential. If it is 0, we say this V1, V2. If the ground sees a jump, let us say by 1 millivolts, this will also jump by 1 millivolt. That was a problem. Now, this will also becomes 1 millivolt. You take the difference, you are set. Correct? So that's the idea. So this is what we call as differential signaling. So instead of having one line, now we have two lines. So this, I'll call it VO of t. This is your single-ended structure. Now instead we have two lines. I'll call it VO plus and VO minus. So VOP and VOM. And the difference between these two is what is defined as my final output VO of t. Okay. Now if I do that, the idea is any noise at the supply will get added on these two lines by the same amount. You take the difference, it gets cancelled. Similarly, any disturbance you have on the ground line will get coupled by the same factor on these two lines. You take the difference between the two, it gets cancelled. Is the idea clear? So typically we do the following. We say it is plus VO by 2 and minus VO by 2 and add a common mode voltage on top. So you have a DC bias. On top of it, you have plus half of the output. On the other side, you have negative half of the output. So if I do that, so let's see what will happen to my interference. So at least we know any issues on the ground and supply lines is taken care of, because any disturbance on these two lines will get impacted on the two outputs in the same way. So it will get cancelled if you take the difference. So let's also see if there is an interference signal like what we discussed here, what will happen now. Let me just copy this. So now we no longer have one output. So I have, let us say, VO plus of t and VO minus of t. Correct? So which means if I make sure that the interfering signal is exactly kept in between, right, I am going to have another capacitance formed between these two. If the spacing between these two lines are equal, what can you say about the capacitance values? They will be same. So which means, let us say here I before had VOP of t plus some alpha times the clock signal getting coupled. Correct? So here what will I have then? I mean, if there is no coupling, I would have just gotten VOP of t. Due to this capacitance coupling the clock, I had alpha times V clock of t. So here what will I have now in the other line? Yeah, VOM of t plus alpha times V clock of t. So once again, if you take the difference, so that's the whole idea. So that's what we do. We make sure that the output is no longer defined as one output line. We have two lines and the output is defined as a difference between the two. So of course, one trivial way to do this is the following. So let us say earlier I had one amplifier. I can say that I'll give plus Vi by 2 here. I'll get my positive output as something. I can take identical copy, give the negative input and get the negative. This is one trivial way to do. So which means if you make it in circuit, you can try to do the, I mean, this might look like this. I have a simple common source, processing plus half of the input. Similarly, I'll have an identical common source, taking the negative half, and you define your output as the difference between these two. Now, although this does the job of what we wanted, there is one major problem here, or a couple of problems. So one of the problems is this, right? See, as I already mentioned, the signal that we might be trying to amplify might be really, really small. For example, let us say it is some 1 millivolts. So which means, let us say the gain is some 20 or something. At the output, you get 20 millivolts. Right? So similarly, here it is, let us say minus 1 millivolt. You have a 20x gain. Now, let us say you have a interfering signal getting added to it, say Vc. At the output, what will I have now? Plus what times Vc? I mean 20 times Vc. So same here. Right? I mean, what I'm saying is the input signal is basically 1 millivolt plus Vc. That's all. And the gain is 20. Again, if you take the difference between the two, the Vc term cancels. But the unfortunate problem is the following. Let us say this Vc is, for example, 100 millivolts. So what will happen to 20 times 100 millivolts? Now your supply is, let us say, only 1 volt. What will happen to the output now? Output will easily saturate. Now remember, this output is not getting saturated because your signal, actual signal is large. Your actual signal differential output is only 40 millivolts. But because you have interfering signal, that also sees the same gain. So which means that the output, this can become 20 times 100 millivolts, which is basically 2 volts. That's a problem. Okay. So this is one main problem. And this is happening because my current amplifier is responding the same way to both my actual differential signal as well as to my common mode signal. In other words, what can you say about the common mode and the differential mode gain here? Both are same. There is no differentiation between whether this is a common mode or a differential mode signal. So if I want to sort of not have this, what do you think my common mode gain should be? Ideally, how much should it be? Ideally, it should be 0. As of now, this particular implementation has the same gain for common mode and differential mode signals. So that's a problem. Now, the solution to this is to have a circuit which has ideally 0 common mode gain. And that's where this guy comes in, the diff pair, where you have an ideal current source here. Correct. Now if I try to do this, so here let us say I have a common mode excitation Vc. Remember, I already have a bias voltage, right? Let's assume that is already there. Okay. If let us say this is current is I0, I have a bias voltage here, When I didn't have this small signal Vc, what can you say about the currents in the transistors? Both are I0 by 2. Now, if I have a common mode excitation added to that bias voltage, what can you say about the currents? So, I mean, if the current is not changing, what is changing in the circuit? Yeah, this source node voltage will change accordingly to keep the current constant. So, which means now even if I go and make any common mode excitation, what can you say about the outputs now? The individual outputs themselves will not change. Again, this is something we had seen. So, here the common mode gain is exactly 0, and that happens if the current source is ideal. Fine. So, to differentiate these two, we have separate names. So, the top structure, which does not have a common mode rejection, is called as pseudo differential implementation. Whereas this bottom one, which has a common mode rejection, is called as fully differential circuit. So, to summarize this fully differential implementation, it inherits all the advantages of differential signaling. That is, it will be immune to any supply ground disturbances and any kind of common mode disturbance, as well as it doesn't respond to any kind of common mode excitation. And there is a term for quantifying the response due to the common mode and the differential mode things. Maybe you have learnt it or heard about this term before. Yeah, it turns out we have just like how we had a power supply rejection ratio that told us how sensitive my circuit is to variations in the power supply. We have a common mode rejection ratio that says how sensitive my circuit is to common mode changes. Again, the definition is same. It's a differential mode gain by the common mode gain. You take the magnitude and show it in dB. Again, ideally, how much do you want this to be? Yeah, ideally, I mean infinity. If I ask ideal, I mean be greedy and ask infinity, right? Someone asks, someone gives you a wish asking for how much money you want. You'll not say 1,000 rupees, right? You'll say all the money in the world. So yeah, that's the solution. So now in practice, that's why all the op-amps that we have will not be a single-ended 5-transistor structure like we have seen so far, although that is also used. There is a 5-transistor OTA. Yeah, this is also used, but a lot of times we prefer fully differential implementation because of all the reasons we saw. So the analogy is, single-ended output is like absolute grading, right? Differential signal is relative grading, right? So if let us say the question paper is really tough, everyone does bad. Absolute grading, you are gone. But in relative grading, you are safe. Just like how here, right? Here, if the ground is completely messed up, in single-ended structure, you are gone. Whereas in a differential structure, because it's difference between the two, will be safe. Right? So I'm sure you will prefer relative grading. So for the same reasons, in circuit, we also prefer differential circuits. Right? So of course, this is the starting point. For fully differential op-amp. Now, we already know the story. This has a limited gain. So to increase the gain, what do we do here? You replace this with the current source, NMOS or PMOS? PMOS. So let's do that. Let's start this. Same old circuits, no change. I mean minor changes. Let's say it's an ideal current source for the time being. So this is connected to some bias voltage, right? So the output is now, let us say, difference between these two. Now before going to any small signal business, let's check what's happening to the DC operating point. So let us say the tail current is I0. You apply some bias voltage on the two sides. What can you say about the drain voltages here? I mean, they'll remain same, yeah, fine, but is it defined? Is everyone find that this drain voltage is not defined? Why is it not defined? Yeah, here we have two current sources. They are biased independently. So even if you by if all stars align properly, even if the currents are equal, this voltage will not be defined. Right? So we encountered a similar scenario in our two-stage OTA. So there, what took care of the biasing? Negative feedback. So let's see if negative feedback takes care of the situation here also, because in our two-stage OTA also we had something similar. This was the first stage, and I had a second stage, let us say PMOS output. So here also this voltage was not defined, but the moment, I think the sign should be like this, the moment I put it a negative feedback, so whatever DC voltage you apply here, that kind of will get set. So let's see if something similar will happen here. Okay, so let's try that. So we'll move to next page. So let me just show the usual one. So let us say here I have a single-ended output op-amp, the same two-stage OTA, let us say, for example. So there again the output voltage was not defined in open loop, but let us say we put it in closed loop like this. So here let us say I connect this to VCM. Here also let us say the input is connected to the same common node. This is R1, R2. Now what can you say about the virtual ground voltage Vx here? VCM? Who's setting this to VCM? Yeah, the negative feedback and the virtual ground is setting it, assuming that the op-amp has infinitely large gain. So which means what can you say about the DC current flowing here? 0. So what can you say about the DC current flowing here? So which means what can you say about the output and Vx? They have to be equal. So if I call this V out, so we call this as V out, because 0 current flows to the resistor R2, my V out will be same as Vx. It is set to VCM. All of this is happening because I have the DC negative feedback around my op-amp, making sure that the DC bias are set. Now let's try to do the same thing with our fully differential op-amp. So in a fully differential op-amp, the deal is this: I no longer have one output, but how many outputs? 2 outputs. So let me draw it like this: 2 inputs and 2 outputs. Now I am attempting to form an inverting amplifier like this. How do you think I can form here? Or here, what was happening when we wanted to make the inverting amplifier? How did we make here? From the output, we had a resistive divider connecting to the input. Now I have 2 outputs. So what should happen? I should have the same resistive feedback on both sides. So let's first draw it on the first side, right? So this is your usual stuff. Now, if I had a single-ended output, it is done. But now I have a differential output, which means the idea is the following, right? We have to sense a fraction of the output and feed it back using a resistive divider. Here it was one output, so one was sufficient. Here I have two outputs, so I should have another feedback network on the other side also.
And so for
Huh.
positive feedback, we will just interchange the
Yeah, correct. For positive feedback, I mean, I can simply change the signs like this. I'll just say this is minus, this is plus. But of course, that's not what you want to do. Is it okay? Right. So now let's see what's going to happen. So as usual, let's assume that the input is connected to some VCM. So let me call this virtual grounds as Vx, Vy. Now the DC negative feedback we have here, that will make Vx and Vy to be equal. So if Vx and Vy are equal, what can you say about VOP and VOM? Both will be same. This is set by your DC negative feedback. Correct? But is my DC negative feedback telling what is the actual voltages on Vx and Vy? Yes or no? No? Because the negative feedback here is just saying that the differential input is 0, which means all I can say for sure is Vx will be equal to Vy, and by extension VOP is same as VOM. But the actual values of Vx, Vy or VOP, VOM is still not defined. Okay? So this is in stark contrast with a single-ended output op-amp, wherein the negative feedback here took care of defining what the voltages are. Is that clear? Again, the other way to see it is the following. See, in this single-ended output stage, single-ended output case, I just had one voltage to worry about. That is one virtual ground voltage or one output. And we had a global negative feedback, and that took care of setting that one voltage. But here, how many voltages I have for the virtual ground? I have two virtual grounds, Vx and Vy. I have one negative feedback. One negative feedback can probably set only one voltage. I cannot expect it to do all the job in the world, right? So, which means the current negative feedback we have is only making the voltages to be equal, or in other words, it is making sure that the differential signal is 0. Or I would say that this feedback is working only for differential signals. That's right? Because it is making the differential signal only to be 0. Correct? So, but I have two voltages, right? Vx and Vy. I have one feedback taking care of the differential signal. So, what should we have now? I mean, I need to define both of them independently, properly. I have one feedback now taking care of the differential part. So, to define the two voltages properly now, what should I have now? I have one feedback taking care of the differential part, right? So similarly, what should I have now? Okay, is this clear that, if I have this particular structure, my voltages are not defined individually, right? And what is getting defined is only the differential part, right? I have two voltages. Differential part is taken care of. To define the individual voltages, in addition to the differential part, what should I be taking care of? So if I have one feedback for the differential mode, what should I have now? Another feedback for? Okay. So which means we need to have a feedback for common mode signals, and that is called as common mode feedback. So this alone is not sufficient because this works only on differential signals. Right? Now we have two voltages to worry about. Again, two voltages you can decompose as differential and common mode. So since a differential mode is already taken care of, you have another feedback working only for common mode signals that will set the common mode of the two. That way the individual outputs are defined. So which means you need to have an additional feedback here. I'll call it CMFB. Okay. Is this clear? Why common mode feedback is essential here? Again, just to make sure, it is clear. If I have, if I have this particular structure, do you think my output common mode is defined here? Yes or no? Why is it defined? Yeah, because the resistor is making sure that, the current is fixed. So VDD minus the drop across resistor is fixing the, here it is okay. The problematic situation comes in practice when you have current sources here. That is where, you have the voltage, both voltages to be undefined. So in that case, you need to have a separate feedback for the common mode signal. Again, you can think of it this way, right? So let's say, let me redraw the circuit here. Or I'll copy this again, hold on. So here, let's say I have a resistive feedback, for example. The right side is the single-ended case that we have discussed so far. So in the right side case where we have the single-ended two-stage OTA, put it in negative feedback. When the feedback was not there, you had two current sources biased independently. But the moment I put the global negative feedback, are both the current sources independently biased or one of them is dependent? What is dependent? NMOS or the PMOS? No, what is getting set? What is independently defined? NMOS or the PMOS? NMOS is independently controllable, and the PMOS gate voltage is set by the negative feedback loop. Right? So if you try to do something similar here, then you will understand what's happening. Sorry. So here, if I were to form the same inverting amplifier, I'll basically do something like this. Remember, I should have the feedback from the, it should be inverting feedback, right? So from the positive output to the negative input and negative output to the positive input. And we already know from the gate to drain is where you have the inversion. So the feedback should come here. So here, although I put the thing in negative feedback, you see that this voltage is still not getting set automatically. You still have independent control on this and the NMOS current source here. Right? So that's why just having the global negative feedback in this particular circuit will not help you. You need to have some other mechanism for setting this voltage, or let us say this voltage. Basically, both current sources cannot be independently biased. Should make sure that one of them is independently biased and set the bias voltage for the other current source based on the first one. So now we have two choices. So let us say this is VBP, VBN. In this circuit, we have two choices. We can either say my PMOS current source is fixed and have a negative feedback loop to tune my NMOS current source, or I will say that my NMOS current source is fixed and have a negative feedback loop to tune the PMOS current. And that's what a common mode feedback loop will do. So let me just show that at a block level, and we can continue from that in the next class. So let us say now I make a choice that I am choosing my NMOS to be fixed. That is, NMOS current is fixed. Okay, I am only going to tune my PMOS current. So now tell me, how do I know if the PMOS current and the NMOS current are equal or not equal? Let us say you have biased the NMOS current to carry a current I0. Now my job is to go and tune the gate voltage of the PMOS so that it also carries a proper current. Right? So again, the whole point of any feedback, what are the two steps to do negative feedback? Yeah, before comparing, what should you do first? We should measure. We should somehow measure the error or some output quantity you have to sense. You have to sense and then compare and finally go and correct. Correct? That's the basic principle of any negative feedback. Right? It's like navigating via Google Maps. You sense where your current location is and then see where the actual location is and then navigate. Same thing. So now tell me, how can you sense if the two currents here are equal or not equal? I mean, ideally, what should be the current flowing here? Yeah. I mean, we'll say ideally it should be I 0 by 2. So let me call this IP. And I want to make sure my IP is equal to I 0 by 2. So how can I sense if IP is not equal to I 0 by 2? What can I check? Sorry? No, I mean in words you tell me, don't go to circuits. First you have it in English, then we can translate that to circuits. Which node you are talking about? This node. But I have two nodes. What should I do? I mean, you are partially correct, right? Because if the two currents are not equal, this voltage will only change. But remember that my feedback loop, I want this to work for differential signal or common mode signal. Common mode, right? So which means what you pointed out is correct. We should look at the output, but I should not look at the actual output. But what part of the output I should look? Common mode of the output. Right? Because the differential output I don't want to touch. So let us say I have VOP, VOM. First thing is I basically detect the common mode. I'll call it common mode detector. Okay. That will tell me the common mode of the output. Now ideally I want this voltage to be a constant value, correct? And typically what do you think might be a reasonable DC bias for the output? Yeah, typically it's better to have VDD by 2 because you have a supply of 0 to VDD. You want to have maximum swings on both positive and negative. So it makes sense to choose the bias to be in the middle. So let us say you have this to be VDD by 2. So which means I have done the sensing part. I have sensed the output common mode by looking at this voltage, but not just the individual outputs, the common mode of the output. Sensing part is done. Now I'm comparing with some reference voltage VDD by 2. Then what should I do next? What should I be correcting? Which voltage here? VB? This voltage we have to change. So basically I should have some block here and that block should go and tune this. Now ideally if things are working, what can you say about my output common mode? I'll call it VOCM. What can you say about VOCM ideally? It should be equal to VDD by 2. Then what can you say about the difference here? 0. And this voltage, will it be 0 or non-zero? This output voltage. It is going to be non-zero. So again, we have a 0 input, non-zero output. What is the gain? I mean 0 input, non-zero output. Gain is? So what gives the infinite gain? Yeah. So you should have some kind of an opamp here. And remember this opamp takes how many inputs and how many outputs? 2 inputs. How many outputs? So this you already know how to design. So basically here I should go and put a single-ended output opamp. So what is missing for the opamp here? Yeah, signs. How do you find whether what is the correct signs? I mean, how do you find? I mean, this should be in what kind of feedback? So how do you check if it is a negative feedback or not? Break the loop. So let me first draw the full circuit so that you know the loop is formed. So this is VOP. This is VOP. So I can break the loop. So where do you suggest we can break the loop now? Okay, I can break it here. That's a good point. As I mentioned, it's easier to break it at the high impedance nodes, typically at the inputs of the op amps or the MOSFETs. What do I do next? Let's say I increase this. Yeah, I can assume some signs. So maybe I'll assume this as negative and positive. So what will happen to the output of the op amp? Output will decrease. So which means this bias voltage decreases. So if this voltage decreases, what can you say about the output voltages? Current will increase. So what will happen to VOP, VOM? They will increase. So each of these two voltages will increase. VOCM will increase. So is it the correct feedback? So which means it should be the other way around, and that basically finishes the loop. Okay, so let's take to the next page and draw it. So which means I should have positive and negative here, and that basically finishes the loop. This way can work. Okay. So this is one way to have a common mode feedback. So in the next class, we'll see the actual circuit implementation of both of them and see if we put all of them together, how it's going to look. Thanks.